and it's going to tell us about scalable machine learning pipelines. Thanks a lot.
All right, great. Well, it's really nice to be here. Today we'll be talking about my work to speed up machine learning pipelines. And so it's a really exciting time to be working in machine learning, in part due to the convergence of various trends. And the first of these trends is that we have access to increasingly large data sets, whether it's from measuring online human activity or from various scientific domains, or from sensor networks such as our phone. A second trend is that we have access to cheap and powerful computing from things like cloud computing or GPUs, both to store and process this data. And third, principled statistical techniques have been developed over the last several decades for a variety of learning problems. And so together, the convergence of these trends really holds the promise for a variety of data-driven applications. And in fact, obviously we're already seeing machine learning being used in our daily lives, whether it's for spam filtering or fraud detection or online advertising, just to name a few. Machine learning is really already being used everywhere. But at the same time, working at the intersection of these trends also introduces new challenges. And I'd argue that scalability is one of the core challenges. After all, classical methods weren't really designed with the scale of modern machine learning data sets. So we know that scalability is a hard problem, but there's a question of why we care. What do we hope to gain from by addressing scalability issues? And I'd argue that there's some core benefits of addressing scalability. So the first is related to feasibility. So data is our core resource as machine learners or data scientists, and we want methods that can fully take advantage of this resource. Second, the more scalable our methods are, the more of the ability we have to iterate on our solutions and refine them and ultimately converge to a higher quality solution. And third, the more efficient and scalable we are, the more frugal we can be with our resources, whether it's time, money, or energy. So with these benefits in mind, the goal of my work is to develop practical methods to enable scalable machine learning pipelines. And to this end, my work really spans theory and practice. Oftentimes, my work is motivated by practical considerations, and I typically develop novel heuristics to address these practical concerns. But once I've figured out a novel heuristic, it's important to study it in more detail, understand its pros and cons, refine it, hopefully improve it. And then ultimately, my goal is to redeploy these new methods back out into the wild for widespread adoption. And so the work that I'll be talking about today has actually gone through this entire life cycle. In the first part of the talk, I'll be talking about a method that's currently being integrated within TensorFlow at Google right now. And in the second part of my talk, I'll be talking about methods that are part of the machine learning library within Apache Spark. So my goal is to enable scalable machine learning pipelines. So I should probably tell you what a machine learning pipeline is. And broadly speaking, I see three components to most learning pipelines. The first component, of course, is the data. This is data which we're going to use to perform some learning task. So for instance, we might have a data set of images. This is a sample from the MNIST data set. And let's say perhaps we want to perform binary classification to predict threes versus not threes. Okay? So we start with our data and a problem at hand. The next broad step is to perform feature extraction. And the idea here, of course, is that we want the raw data that we have, let's say pixel representations of data, might not be the best representation for the downstream learning task that we want to perform. So in the case of images, perhaps we want some higher order representation, say edge detectors or several other sorts of feature extractors. So now once we have this representation of our data, we're ready to perform model training. And so for this particular example, this is going to be learning a supervised binary classification model. Perhaps we're going to learn a linear classifier. So these are the three core steps of a learning pipeline. And so the question is, where are the core bottlenecks here? And so one thing to note is that modern pipelines have several knobs to tune, both in the feature extraction and the model training steps. And these knobs properly tuning these knobs is crucially important to training a pipeline with high accuracy. And so searching this potentially high dimensional search space can be a significant bottleneck, even for modest sized data sets, as it can require training tens to thousands of pipelines. And the situation is more difficult when we're working with large data sets, where in this case, typically the model training step is the real bottleneck, as we have to perform multiple passes over our data. And so when we have really large data sets, what we typically want to do is leverage parallelism both to store and process the data. But in doing so, figuring out how to effectively and efficiently train in distributed settings leads to novel communication and computational concerns. So today I'll be talking about my work for both of these problems. Before I dive into the details, I want to give a little insight in terms of the strategies that I take to try to solve these problems. And so my approach is fairly intuitive in my opinion, and it really just involves sampling. And this can be sampling of data points or features or other artifacts of a machine learning pipeline. And from a computational perspective, this makes a lot of sense, right? Working with subsets of data, of course, is going to be faster than working with all of our data. But from a pushed the wrong button. But from a statistical perspective, it's not really clear what the impact of sampling is going to be. Right? So after all, statistical inference relies on aggregating across data. And now when we introduce computationally modeled sampling schemes, it's not clear how that's going to impact our desired aggregation and pattern recognition. So how do we resolve this tension? Well, so in my work, I found that there are generally two approaches that seem to work well. In the first case, we can devise new methods where we carefully align the statistics and the computation such that we can hope to get the best of both worlds. We can get an efficient parallel execution of our algorithm while still returning a serial equivalent result. So this is sort of the best case we can hope for, but it's not always possible. And so when we can't do this, we alternatively have to develop new approximation algorithms, but then we have to carefully study them practically and also theoretically to understand the quality of these approximations. Okay, so let's dive into the first part of the talk. And of course, please feel free to ask questions along the way. The first part of this talk of efficiently searching this design space, this is joint work with collaborators at UCLA, Berkeley, NYU, and Google. And I'd like to particularly highlight the contributions of my student, Leisha Lee, and of Kevin Jameson, who's a postdoc at Berkeley. All right, so let's understand this problem a little bit more formally. And to do that, let's go back to this running example of this MNIST data set. Right, so imagine we want to, again, perform some sort of classification task to distinguish between these different digits. And to do that, we want to find a pipeline, a highly accurate pipeline within this design space that's parameterized by knobs or hyperparameters. Right, so there's a question then of what are these hyperparameters that define this hyperparameter space? And the first question, the first hyperparameter we have is the model family we want to choose. So in the earlier slide, I talked about using a linear model to predict between threes or not threes. But we could use other models as well. We could use a decision tree or a random forest or a neural network, several different classification models. Let's say for the sake of this example, we're focusing only on neural networks. Right, but even if we fix the model family, there's still several other hyperparameters that we have to tune hyperparameters we can tune related to the structure of this neural network that we want to learn. But now that we've defined this hyperparameter space, we now want to see the quality of particular configurations within this space. So let's assume we pick a particular configuration and we want to evaluate how well it's performing. So how can we do this? Well, the standard way to do this is to take some training data along with this configuration and plug it into some black box solver to spit out a trained model. That's what I'm referring to with this FHAT. And now once we have this trained model, we can evaluate it on held out data set and get some predictive error. Right? But we don't want to do this just once for a single configuration. We actually want to repeat this process over and over again. So we try this with a second configuration and get another predictive error. We do this for a third configuration, and so on. And we keep doing this until we've exhausted our budget or we're happy with an answer that we have. And ultimately, what we return is going to be the configuration which has the lowest error. Right? So in summary, the problem that I'm interested in solving is how can we efficiently identify high-quality hyperparameters? And here by efficiency, I mean we want to minimize the total number of resources that are consumed. That could be time or some other resource that we're interested in. And then in terms of quality, I want to find a configuration that's of high quality, that has low predictive error. OK, so how do people typically do this in practice? Well, the typical methods for hyperparameter optimization focus on different ways to select configurations to evaluate. And the most common approach is straightforward random search. So here is a picture of a two-dimensional hyperparameter space where these the red spots are the hot spots in the space corresponding to configurations that are of high quality. And so with random search, what we do is just randomly sample from our predefined design space. And for each one of the points that we sample, we evaluate it using the procedure I just defined. An alternative approach that people have been studying a fair bit in the last few years is an adaptive approach. And in this adaptive approach, we first start by randomly sampling and exploring the space, hopefully getting a coarse covering of the space. And once we have this coarse covering, we then want to be greedy and iteratively select subsequent points that we think are more likely to lead to good configurations. So if things work out well, we're going to iteratively and sort of learn from our past experience. Hopefully, we're going to select configurations that are sort of concentrated around these hotspots, as I showed in this picture. All right, so let's understand the pros and cons of these methods. And to do that, we're going to assume that we're working with a hyperparameter space of a d-dimensional hyperparameter space. So we have d hyperparameters to tune. And we're assuming we have a budget of n pipeline configurations. So then there are two cases that we can consider. In the first case, n is exponential in d. So that means we have an exponential number of hyperparameter configurations that we can evaluate relative to the number of hyperparameters. And this is a great situation for us. So we know that the volume of this hyperparameter space is going to be exponential in the number of hyperparameters. And if we have roughly the same amount, roughly an exponential number of configurations that we can look at, we actually can hope to satisfactorily explore the space and cover it. And random search should do pretty well. Sorry. Right, so we can hope to cover this space. Similarly, if we can cover this space, that also allows us to do a coarse cover via adaptive sampling before we try to greedily find better options. So adaptivity works well here as well. So this is a good setting to be in. But there's a second setting we can consider, which is the case where the number of configurations we can consider is actually linear in the number of hyperparameters. And unfortunately, this setting is much more challenging. Right? When the number of configurations is linear, we can't hope to cover the space. If we can't even hope to adequately explore or cover the space, there's really no point. It really limits the degree to which we can be adaptive as well. Right? And unfortunately, this is an increasingly common regime, where more and more of modern data sets, we're looking at complex pipelines. So these pipelines have more and more hyperparameters. And as our data sets get larger, evaluating a single pipeline can be more expensive. Right? So this is an increasingly common regime, and the current sort of state-of-the-art methods are not really well suited here. So what can we do? Right? So our idea is to rely on downsampling. And the idea is effectively to downsample to allow us to evaluate more configurations or boost basically n while still working on the same budget. Right? So the next question is then, what should we be downsampling? And our observation is that many learning algorithms are iterative. So in particular, gradient descent and other first-order optimization methods, those are the primary examples, but there's others as well. And so perhaps we can try to downsample iterations. Right? So let's see how that would work. So here we have a plot. The x-axis is the number of iterations. The y-axis is the predictive error. And so basically, we're going to track the predictive error for different models as a function of how many iterations we've trained them on. Right? So here are traces for a bunch of different models. And remember, the goal of this problem is to try to find each one of these corresponds to a configuration, and our goal is to find the best configuration, or a very good configuration, so one with low predictive error. So thinking about our high-level goal in mind, with our high-level goal in mind, it sort of seems like we're kind of wasting iterations here, right? After a few iterations, it already seems like some of these guys aren't really going to be serious competitors. So it doesn't really matter what they converge to if they're not going to be high quality at the end of the day. So why are we wasting resources training these suboptimal methods all the way to completion? Instead, it seems more reasonable to focus our efforts on the subset of the competitors that are really possibly going to be the best ones. Right? So, yeah.
So how is it possible that if you have very deep neural network and the deeper neural network will take more iterations to converge, but will have lower error?
Right. Okay. So there's 2 points here. So I would say, one caveat to this work in general is that if you're working with different model families where they converge at orders of magnitude different rates, then you're going to be in trouble. The way to get around that would be to sort of apply algorithms like this separately on different model families where the convergence is at least the same order of magnitude. But in terms of this idea of, like, say this guy, maybe it did nothing, but then it actually zoomed down even further. If they're even roughly in the same order of magnitude, what your question is exactly highlighting the problem of naively performing this approach. How do you know how to do this safely? Right? So that's exactly sort of my next slide. It's a good question. Right? The picture that I showed before is sort of a simple case where things are well behaved. But right, these sequences could sort of be not very well behaved. They could be non-monotonic, non-smooth. And the real question is how we can safely discard a configuration. How do we know when we can actually stop when we've seen enough? So that's right. And so hopefully I'll answer your question in the next few slides as I present my method. Right? But for the last few years, I've been studying this problem of how we can safely discard iterations, right? Make formal this idea of downsampling. Right? So we presented Hyperband. This is a novel downsampling approach. And as I'll show you, Hyperband achieves state-of-the-art empirical performance for a wide range of hyperparameter optimization tasks. And it's also provably correct. So we can show that it's safe in some sense in terms of how we discard configurations. So there's 2 components of Hyperband. So let me explain each of them in turn. The first ingredient is successive halving. It's really more like, it should really be called successive thirding, but successive halving sort of has a nicer ring to it. And the idea here is that this is sort of the way we want to adaptively allocate resources to a given set of configurations. This is the scheme that we're going to be using. So let me explain this with an example. And again, the x-axis is the number of iterations, the y-axis is the predictive error. And for this toy example, we're going to assume that we start with 9 configurations. And at the start, we're going to allocate to each of these 9 configurations 9 iterations, so some small budget. And then we're going to evaluate each of them. Right? So each of these triangles correspond to each of the 9 configurations, trained for 9 iterations. So that's here x equals 9 roughly. And then we perform a thirding, which basically means we draw a line and we keep the best 3, throw out the rest of them. And then we continue this process. Now we only have 3 active configurations. We allocate additional resources or iterations to them, and we then compute their predictive error, and then do another thirding. So now we only have 1 left, and we allocate additional resources such that we train it to completion, and this is the answer that we're going to pick. So basically what we're assuming here is that we're training each model for a max number of configurations, and here that max number of configurations is 81. We're calling that R. The total budget, the total number of iterations we've allocated across all of these configurations is 5R, which is the equivalent of training 5 models to completion. But we started with 9 configurations, n equals 9, so we are doing some sort of downsampling here. As on average, we're allocating 5/9 R configurations, 5/9 R iterations to each configuration. So you might be asking, maybe this is a reasonable way to allocate resources across these different configurations, but it's not clear that it actually deals with this issue of safety. And if that's what you're thinking, you're exactly right. Right? So this is the same picture, but now let's consider this red triangle here. And we stopped it early because it wasn't in the top 3 at our first round of decision making. But who's to say it wasn't just a late bloomer, exactly to your point. And maybe, had we trained it for longer, it would have converged to the best answer. And the fact of the matter is that it's hard to know this a priori. But the more we downsample, the more we increase n, the more we're able to explore the space, which is a good thing, but the more likely we are to introduce errors. And really the right value of downsampling, the appropriate amount of downsampling, really depends on unknown convergence properties about each of these configurations. So it's sort of a hard question. So what should we do? So that leads us to the second ingredient of this algorithm, which for lack of a better term, I'm describing as safe downsampling. And so what do I mean by that? This table here corresponds to different variants of successive halving with different amounts of aggressiveness in terms of how aggressively we're downsampling. Right? So we start on one, right? So I'm calling each of these different schemes a different bracket. So all the way on the right here, we have the most conservative bracket where we start with 5 configurations and we train each of them to completion. So we're not doing any downsampling. This is just vanilla random search. On the other extreme, we're being as aggressive as we possibly can, subject to the constraint that we want at least 1 configuration to be trained to completion. So here we're starting with 81 configurations, providing a resource of just a single iteration before throwing out a third of them. Right? And these other brackets are somewhere in between. This middle guy is the one that I showed the example about earlier on. Right, so let's see how these perform in practice. Right, so here the x-axis is time. Again, we're showing predictive error. And these are empirical results on this MNIST data set, tuning hyperparameters to the classical LayNet neural network with 4 hyperparameters. So first, let's see how this initial bracket where we start with 9 configurations, how it looks. Right? And we see that the predictive error decays over time. But who knows? Maybe we were being too aggressive and we shouldn't have downsampled quite as much. Right? So we can try a different bracket where we now only start with 6 configurations. So we're barely doing any downsampling. It turns out that this doesn't quite perform as well. Again, lower is better here. And just for curiosity, we can see how random search would have done. And it turns out that being even more conservative was not good for this particular problem. So in contrast, we could try to be more aggressive than this first bracket s equals 2 that we tried. And we can start with 27 configurations instead of 9. So let's see how that works. Turns out that gives converges to a slightly better answer, and it gets a good answer more quickly. So we can really try our luck now and maybe be even more aggressive. Unfortunately, doing that now leads to a suboptimal answer. Right? Now we've gone too far. We've been overly aggressive. And the point here, again, is that the optimal choice of which bracket to choose is unknowable a priori. It's going to be data set specific. So our approach, our idea is, let's try all of these different brackets. Right? Let's hedge. Let's not say one of them is the best. Let's try all of them. And that's the idea of hyperband. Right? So with hyperband, we basically alternate between, we search the space of the number of initial configurations that we want to look at in log. We do a grid search in log space. So overall, we basically try 4 or 5 different brackets instead of 1. And the idea is that our goal is not to beat the best bracket in hindsight, but the goal is to be not much worse, and to do so in a safe sort of fashion where we can guarantee that we're not going to be overly aggressive. Okay, so this is how hyperband. Or any questions on the algorithm before I show some results on it?
Did you say that hyperband samples the hyperparameters randomly, or can that use?
Right. So I haven't really talked about that. Right. So so far the way we've been looking at it is exactly as a way of just speeding up random search. So you could try to also apply adaptive search techniques and combine it with that, and I think that's a really interesting avenue of future work. We haven't really looked at that yet. But basically, our idea in the algorithm, in terms of as well theoretically what we want to show about things, is to say, hey, we know that random search is ultimately going to work. We want to see practically what speedups we get by just sort of speeding up random search via downsampling, and we also want to understand sort of theoretically how it's going to perform theoretically relative to something like random search. Yeah. Okay. Right. So these are results on a toy data set. Let's see how things look on slightly more interesting data sets. So this is a result. We're again tuning a neural network, but here this neural network is it's a larger 4-layer CNN with 8 hyperparameters. It's using a slightly larger benchmarking data set, this SAFAR data set, and we're x-axis here is the number of iterations. Y-axis again is predictive error. We're going to be training a bunch of these different models to a final budget of 50 R, which is the equivalent number of resources needed to evaluate 50 configurations to completion. All right, so first, this is how random search performs. We also tried a bunch of different adaptive methods for various data sets, and there wasn't one clear winner among the adaptive choices that we tried. So here I'm just showing the best of the adaptive methods for this particular benchmarking experiment. I think it was a method called SMAC early. Right, but so this is how how SMAC early looks here, and then this is how hyperband looks. And sort of the key takeaway here is that after a budget of 5 R iterations, random search and this adaptive method have each looked at 5 configurations. Right? Random search has randomly picked these configurations. The adaptive method has done something a little clever in terms of how to pick the configurations, and actually at the beginning it doesn't do much, but then it drops down. But in contrast, hyperband, after a budget of just 5 R, has actually considered 256 configurations by leveraging downsampling. So it's been able to explore the space a fair bit better, and it's achieved a much better result. So we see here a speed up of over 50x relative to random search, speed up of 10x relative to this adaptive method. And on average, we tend to find that hyperband converges to a lower final error. This isn't always the case. Sometimes the adaptive methods match us. But on average, we tend to be converging to a slightly better answer. And importantly, we also have much lower variance than these other methods. And so what I mean by that is these experiments are averages over, I think, 10 trials. And the variance across these different trials is very small for hyperband relative to these other methods. And that's not really that surprising, given that hyperband is considering many more configurations than these other methods. OK, so that's the basic idea of how the algorithm works. But we've explored a bunch of extensions to the algorithm as well. And one extension is sort of, what do we do if we're really impatient? And what I mean by that is, I don't mean to be facetious. I mean that it could take a day or a week to train a single model. And we might have hyperparameter spaces where, at the least, we want to consider, say, 50 different configurations. And so if you did this serially, 50 models where each of them takes a week, that's roughly a year to do this serially. And that's way too long to train to do hyperparameter optimization. So what can we do? Right? So a natural thing to think about is trying to parallelize this search. It turns out that the approach that I described earlier, the vanilla hyperband approach, isn't really amenable to parallelization. There's going to be a lot of idle computation as you do later steps of this successive halving method. But we do have a variant that's much more amenable to parallelization. And we're collaborating with folks at Google to integrate this parallel method into TensorFlow. So this is just, this is ongoing work, and this is just one result that we have here. This is, again, using the SAFAR data set, but on a residual network with 16 hyperparameters. And the key idea here is that now, instead of training on a single machine, we're training on 50 workers. And moreover, it takes over a day to train a single model here. But we still want to return an answer in the time that it takes less to train, in time less than 2 full training cycles in the serial setting. Right, so in the time it would take a single machine to train 1.6 of these models, we want to return our answer. So we want to get our answer very quick in terms of wall time. Right, so we can, as a baseline, look at random search and see how it performs. And in contrast, we can evaluate our parallel version of hyperband. And so how good is this result? Well, the difference in error is just 3%, which may or may not sound like a lot, but for this particular benchmark, it's the difference between a pretty good result and getting state-of-the-art performance for this network. So it's a significant result, and we get it very quickly. Okay, so another question we've looked at is, how does this method actually work theoretically? And to study this, we've been able to frame this problem as a multi-arm bandit problem. And so that, a natural question we can ask here, or a natural problem we can study, is this best arm identification problem. And so the idea is that given n hyperparameter configurations, how many resources, say iterations or time, are required to find the best of these configurations? Right, so that's a question that we want to solve. And there are two quantities of interest when thinking about this problem. Neither of these quantities are actually going to be known to us, but they help us reason about the problem. Right, so I'm going to explain them via a picture here. So again, as with the other plots, the x-axis is number of resources, the y-axis is our error. And this is a trace for a particular configuration. And our first assumption here is that the limit of this trace exists. So that we're saying that this trace is going to converge to some limiting value. And this is a fairly minor assumption, especially when we assume that we're training each model to a maximum number of iterations. We know that this limit value is really just going to be the validation error of the model trained to completion. So this is quite a minor assumption. But by making this assumption, this implies the existence of these envelope functions. And these envelope functions, these gamma k's, they bound the uncertainty of these intermediate results. Right? So this is a picture for a single configuration. We can draw pretty much the same picture for a different configuration. And we see here that this configuration 1, is better than configuration 2 as it converges, as nu1 is smaller than nu2. And so then the question that we want to answer is, how many resources, or when can we stop allocating resources to nu2? When can we know for sure that we can distinguish between this second configuration and this first configuration? And intuitively, the idea is that once the gap between nu2 and nu1 is greater than the width of this envelope function, then we're in good shape. And so that's exactly what this gamma inverse function gets at. Oh, the colors are a little off. Basically, we can stop allocating resources to this suboptimal configuration once the uncertainty defined by the envelope function is less than the distance between these limit points. And of course, it's important to note here that this problem is harder if nu2 minus nu1 is smaller. Right? Then it's just harder to differentiate between them. And the problem also is harder if these envelope functions are wide, meaning if there's more uncertainty in the intermediate results. Okay. But so now that we have this gamma inverse, we can start to state more formally how different methods perform in terms of allocating resources for this best arm identification problem. Right, so first we can think about uniform allocation. And uniform allocation is exactly what random search is doing. For all the n configurations that you have to allocate the same number of resources. Right? And this uniform allocation is hamstrung by the worst case. If there's a particular iteration where you have to allocate a lot of resources to differentiate it from the best guy, well, then you have to allocate that same number of resources to all the other configurations as well. So you get n times this max. In contrast, for successive halving, it's a much more attractive, we can use much fewer resources. And the idea here is that we have a sum over these gamma inverse functions. And the reason that's nice is that if there are some configurations where it's really easy to differentiate suboptimal one from the best one, and the best one here is nu1, then there's an associated gamma inverse term associated with that particular configuration. We can allocate just a few resources and throw it away. Right? So in general, if n times the max versus the sum, the difference can be quite large. And in fact, if you think about it, you can't really do much better than this. Modulo this log factor, you need to allocate gamma inverse iterations to each configuration to know for sure that you can differentiate between the two. Right? So successive halving is nearly optimal, which is really nice. But the one issue is that we have this bound for the number of resources that are required for successive halving to work, but this bound is dependent on gamma inverse and the nu i's. And these are values that we have no idea about. Right? Gamma inverse is the uncertainty in the intermediate results. The nu i's are the limiting values that actually we care about in the first place. So this bound really isn't very actionable because there's no way to know this oracle information. So roughly speaking, what we're able to show with hyperband is that we can get within a constant factor of this same budget without using an oracle, using hyperband. And that's just by trying a few different variants of successive halving. So that's sort of a summary of the theory. All right, so any questions before I move on to the second half of the talk? Okay, so we just talked about searching through this design space. So in the second part of the talk, I want to focus on scalable model training. The focus here is that we want to figure out how to handle massive data sets, how to learn in the presence of massive data sets. And my work has been focused on addressing this problem in a distributed or scale-out setting, where the idea is that, in a scale-out setting, cloud-based setting, in other words, and this setting has a lot of it has attractive features in the sense that it relies on commodity hardware at each node, and it can really scale to massive problems. As your problem gets bigger, you can just add more nodes to your network. So this is nice, but there's also drawbacks of this distributed setting. One, network communication is typically much slower than, for instance, multi-core settings. And second, there's, of course, added algorithmic and software complexity to sort of coordinate the efforts of these different nodes. Right, so over the last decade or so, I've been developing and studying different methods in this distributed setting. I've worked on problems related to kernel methods, manifold learning, collaborative filtering and robust PCA, quantifying predictive uncertainty, and fairly recently, genome sequencing processing. But the common thread to all of these works is this idea of using sampling to reduce bottlenecks. Right? And the sampling can come in various forms. You can subsample data points. You can use efficient or well-studied single machine algorithms and embed them in computationally motivated divide and conquer frameworks. I've also considered dimensionality reduction or feature selection methods when dealing with high dimensional data sets. But what I want to talk about today is using some of these similar ideas, using some of these same ideas for problems related to decision trees and ensembles of decision trees. So ensembles of decision trees, they're very popular in practice. They're highly accurate, highly robust. You could argue that they're sort of the first tool in a data scientist toolkit. As an example of this, I think in Kaggle competitions in the past year, gradient-boosted decision trees, which are a particular type of ensemble method of decision trees, were the most popular method used in winning submissions to Kaggle competitions. So people like them a lot in practice. But they also suffer from various scalability challenges. And in some recent work, I've been looking at different sorts of scalability challenges related to decision trees. So the first question I've looked at is the simple question of just how to train a single decision tree in a distributed setting. And a second challenge I've looked at, or second problem I've looked at, is in the context of interpreting decision trees as a form of local learning. And I'll talk more about that a little bit later. All right, so let's talk about this first problem of distributed training of decision trees. This is joint work with a bunch of collaborators, and in particular, Faraz, Joseph, and Mate. And so, how do people currently try to train decision trees in a distributed setting? Well, the sort of state-of-the-art approach, and this was introduced by folks at Google, I think in the late 2000s, is based on a row partitioning approach. And the idea here is that you have your n data points. They're too large to fit on a single machine. So what you do is that you partition this data, have each worker store a subset of the data points. And on a high level, when training a decision tree, what you want to do is for each intermediate node, you want to split it into two child nodes. And you want to consider a bunch of putative splits to make the best greedy choice for your split at that intermediate node. And so what this row partitioning approach does is it considers all candidate splits, and each worker computes some intermediate information for each of these splits and sends it back to the master. So this is clearly a divide and conquer algorithm of sorts, but it's not a super efficient one in the sense that it incurs really high communication costs. Right? These communication costs are exponential in the depth of the tree and linear in the number of the features. And in addition, in order to make the communication reasonable to some degree, approximations are required. So in a serial setting, when training a decision tree, you typically consider n times d possible splits. So n splits for each possible feature. But in this distributed setting, that just would lead to way too much communication. So what people do is they consider a constant number of splits for each feature. So it's O of d instead of O n d. And in practice, this approximation actually does work reasonably well. But it still is the case that when training in a distributed setting using this approach, you get a different answer than you would have had you trained in a serial execution. So in recent work, we've proposed an alternative approach. We call it Yggdrasil. Yggdrasil is a mythical Norse tree. It's very, very large. And this method in particular works really well as trees get deeper. So the name is somewhat apt, if hard to say. Right, so the key idea here is that instead of using row partitioning, we use column partitioning. So now our data, each worker, instead of storing a subset of the data points, it stores all the information about a subset of the features. And crucially, this method is sort of an example of where we redesign the algorithm such that the computation and the statistics are well aligned. By having each of the workers store all the information about a subset of features, each of these workers can do a lot more work locally before having to communicate back to the master. And in particular, the worker can figure out the best possible split for each feature and then find among all the features that it's storing which of the features is optimal. So it does a lot more work and then sends much less back to the master, and as a result, it's much more communication efficient. Right, so how do these methods compare in practice? Sorry, I should also say that by partitioning this way, we're now able to consider all splits and get a serial equivalent execution, which is nice. Right, so let's see how these methods work on some real data. So I'm going to show results on a Yahoo data set. And in fact, folks at Yahoo were kind of the motivation for us working on this problem in the first place. They were early adopters of the machine learning library in Spark MLlib, but they weren't really happy with our row partitioning implementation of decision trees, as it just didn't scale well to the data sets that they had. So this is one of the data sets that motivated this problem. It's a regression task with roughly 50 gigabytes, 2 million points, 3,500 features. This plot that I'm showing on the x-axis, where I'm going to show the time it takes to train various trees train trees to different depths. So these are results in Spark. The red line here is the row partitioning approach. That's the default in MLlib. And what we see is that it works fairly well up until depth of around 12, and then it kind of blows up exponentially. And this is just due to high levels of communication. And in contrast, we see that Yggdrasil sort of matches performance for trees of small depth, but then it does much better as trees get of higher depth. So we see up to 24x speed up for deeper trees. And across various benchmarking data sets that we looked at, we see that we get the largest gains when the trees are deep and when we have a lot of features. So our next step for this particular problem is to push our implementation of Yggdrasil or integrate it within MLlib, which is again this core machine learning library. And I want to spend a few minutes talking about MLlib. As a postdoc, I led the initial development of MLlib in the AMP lab, working with some systems students at Berkeley. We shipped it as part of Spark back in a very early version of Spark in 2013. And just in a few years, the adoption has been was amazing to see. It went from a small group of contributors to over 150 contributors from a variety of companies. Right, and this is just ending in 2015. Since then, Spark clearly has outgrown being an academic project. It's being commercialized by a bunch of companies and maintained by them. But along the way, it's been a really interesting experience, both from a research and educational standpoint, working on MLlib. So first, as part of this exercise, we developed some state-of-the-art distributed methods for decision trees, which I just talked about, as well as for large-scale collaborative filtering problems. I also used my experience developing MLlib and about distributed computing to teach a MOOC on the edX platform called Distributed Machine Learning with Apache Spark. So I think partly due to the timeliness of machine learning in Spark, it was a really well-received MOOC. Students got to learn about principles of distributed machine learning and get their hands dirty with Spark, which was kind of interesting to see. Okay, so in the last part of the talk, I want to briefly talk about scalability challenges related to an interpretation of decision trees as local models. So what do I mean? Actually, I should say, so this is joint work with my student, Chris Wu, as well as Adam Blanyarts when he was a student at Berkeley, Arash Amini, who's a professor at UCLA, and Ben Yu, who's at Berkeley. So what are local models? Right, so it's hard to see. This is training data, and then there's a bunch of little training points here. Right, so in contrast to sort of global models, where you do a lot of work at training time to learn one single model, in local learning, you don't do very much at test time. You're sort of lazy. In the computer science world, this has also been called lazy learning for that reason. What you do basically is at test time, you find a neighborhood. You find your local neighborhood in your training data, and you use that neighborhood to train a local model, and then you make a prediction from that model. Given a new test point, you do the same thing. You find a separate local neighborhood, train a local model, and you make a prediction. Right? And sort of the simplest example of this is k nearest neighbors. Right? You find k neighbors for every test point, and typically with KNN, you use a local constant model. You just take, if you're doing regression, say, you just take an average over the k training points, and that's the prediction that you make. But you don't, in fact, need to use a local model. You don't need to use a constant local model. You could use a more complex one. And in fact, local linear models have been well studied in the statistics literature for the last several decades, and they've been shown to have some really nice favorable properties. So they generally have improved accuracy over constant models. And they also, they inherit the interpretability from local methods, or from linear methods, excuse me, right? You have a single weight on each feature. It's fairly easy to interpret them. So they're really nice in low dimensional settings, but they suffer from the curse of dimensionality. It's really hard to find neighbors in high dimensional spaces. You need a lot of samples. So, what can you do? Right, so how can we avoid this curse of dimensionality? Right, there's sort of two things that you can do when trying to find neighbors or when working with high dimensional data in general. One is that you can assume that you have a small number of active features. This is a common assumption people make. If you don't make this assumption, learning is just incredibly hard as you have very high dimensional data. And then, assuming that when you make this assumption, you then naturally are going to want to identify your neighbors, not just based on the features, but based on features and labels, such that you can hope to learn neighborhoods that are really focusing just on these active features. And there have been some classical works that have tried to do this, but for the most part, they've been computationally intractable for more than, for anything other than very small data sets. But it's also been noted, and this is work by Lin and Jian in 2006, that decision trees and random forests can also be interpreted as learning supervised neighborhoods. Right? So in particular, when you have a data point and you drop a test point and you drop it through a trained tree, the neighborhood for that test point is really just whatever leaf it ends up in, and the training point's associated with that leaf node. Right? So the leaf nodes of a tree are supervised neighborhoods. The tree is learned in a supervised fashion. So we're kind of doing exactly what you kind of would hope to do. We're learning neighborhoods in a supervised fashion. But at the same time, the predictions from a decision tree or from ensembles of decision trees are generally local constant models. Right? The norm is to take an average over, just take an average if you're doing regression over the training points in a particular leaf node. So the idea of our work is to try to get the best of both worlds and combine these two ideas. Right? So to combine the favorable properties of local linear models in low dimensional settings, right, highly accurate and interpretable, with the benefits of random forests in high dimensional settings. Right? They can be viewed as supervised neighborhoods to find the neighbors in the first place. There's one caveat here, which is that if you want to use a random forest to find neighbors and then train a local linear model, you're still left with this high dimensional problem when training this local model. But it turns out what we've been looking at is that you can use the random forest itself to do a form of variable selection, to now train the local model on a subset of the features. So combining these ideas together gets us to our algorithm, which we're calling Silo, and this is sort of an active area of research for me. So just to give you a short glimpse of how it works in practice, these are results on a subset of data sets. We've looked at others, but this is kind of what fit on the slide. I've also tried a variety of competitors, but these are kind of natural ones to try. The first is a random forest, which is what Silo is built off of. The second is Lasso, which is itself doing some sort of variable selection. And these are all regression tasks, so I'm going to be showing RMSE, lower is better. And what we see is that when comparing Silo to a random forest, it's better than the random forest across all of these problems, and in some cases by a fair bit. And it also has in my mind, the important benefit that Silo is much more interpretable than a random forest. Right? Whereas a single decision tree, you can argue it's interpretable. An ensemble of decision trees is often very difficult to interpret. So Silo both boosts the accuracy, but also makes it much more interpretable, which is nice. And then relative to Lasso, we beat the Lasso on all the data sets, except for this one linear data set, which is a synthetic data set, which is exactly matching the assumptions of Lasso. So it's not surprising that Lasso does better, but in fact, Silo's not doing too much worse, which is encouraging. Okay, so I'm about to wrap up. I just wanted to, in the last few minutes, just remind you guys summarize what I talked about and tell you a little bit about some of my plans for future work. Right, so the goal of my work is to develop practical methods to enable scalable learning pipelines. And in the first part of the talk, I proposed Hyperband, sampling-based method for hyperparameter optimization and to explore this design space of pipelines. And in the second part of the talk, I focused on how to train models in distributed settings, and with a focus on decision trees. And moving forward, I think there's a lot of really interesting problems and open problems to study in this area of scalable learning pipelines. So one interesting problem, I think, is to look at the two problems that I talked about today, hyperparameter optimization and parallel model training, and to think about them in a more holistic point of view. So at the end of the day, the problem that we often have is that we have a lot of data, we have a lot of distributed computing resources, and we want to get a good model trained as quickly as possible. So given some finite computational budget, there's a natural question of, should I parallelize hyperparameter optimization? Should I parallelize distributed training, or should I parallelize both? There's also a question of how can I reuse computation as I explore the search space, because there's definitely computations that you're performing multiple times. And in particular, I've been studying this problem recently in the context of deep learning, as the design space is usually quite large. There's a lot of hyperparameters, and training deep learning models in distributed settings is generally a very high communication endeavor. All right, so a second interesting problem is, so in this talk, I focus mostly on the model training part, how to learn a new model or a new pipeline. And of course, that's a challenging problem. It's really important. But once you have this pipeline, you actually need to do something with it. You want to use it to make predictions. So there's this question of how to actually serve these predictions and how to do this efficiently. Of course, this is an important question for the local models that I've been studying, as there's a lot of work that you have to do at test time. It's also a really interesting problem, in my opinion, when trying to make predictions on remote devices, and in particular our cell phones. So how can we do this more efficiently? How can we quickly make predictions on cell phones? So that's another interesting area. And a third area that I think is super interesting is thinking about where our data comes from. Right? So in general, the field of large-scale ML, up until recently, is largely focused on how to train in multi-core settings or distributed data centers. But our data isn't being generated by and large on these data centers. More and more, it's being generated by our cell phones or smart homes or other smart devices. Right? And these devices, our cell phones in particular, are really powerful machines. And for various other reasons, privacy or battery, or just to decrease latency, it's interesting to see how we can train directly on these heterogeneous devices rather than moving everything to a centralized cluster. So that's another problem that I'm actively looking at. All right, so with that, I'll conclude. Thank you.
Yes. For MLB question, what do you think would be the bottleneck for MLB?
What is it?
So performance or
So I think one bottleneck for MLib, or just generally learning, so a lot of the work that I've done has been on distributed computing platforms, and it's great because it scales out, but communication is a huge bottleneck.
Right.
And so it's not the solution for everything. If you don't need to go to a distributed setting, if your data can fit on a one beefy multi-core machine, in many ways your problem is going to be a lot easier.
Yes, so last year when I was at RCML, the Machine System Conference, I heard a comment saying that for MLB, the model size is kind of limited. Like if you have a few megabytes, that's probably okay, but if you go larger, tens of 100 megabytes, probably either crash or take very long to run.
Right. So are you worried about the model doesn't even just fit on a single machine, or
no,
just?
I'm worried about does it scale to larger models?
Right. So I think model parallelism is not something it's not a general purpose. Right. That's one way to scale, and it's not there's not general purpose functionality in MLlib for model parallelism. Though some for instance, our collaborative filtering approach is a model parallel approach. So yeah, I think
the way I'm thinking is
yeah.
Broadcasting. So basically, there are two ways of doing communication.
Right.
One is you can broadcast. They are doing RTD joins.
Right.
Broadcast is basically limited by the size.
Right, and by doing joins, you're sort of doing a model parallel approach.
But
right.
Joins are very expensive.
Right. So at this point, there are going to be limitations. Right. So I'm no longer actively developing MLlib. At this point, there's several companies doing that, and I'm letting them do that. At the point that the way I looked at it was, I agree, the broadcasting becomes an issue at a certain point. And the question, when I was last working on MLlib actively, it was in 2015, the question that I would get all the time, deep learning, why is deep learning not being used, or why is deep learning not implemented in MLlib? And it's exactly for that reason. There's just, you're not doing enough work per iteration to warrant the amount of communication you have to do when you want to broadcast the parameter vector at each of these iterations. But I would also say that for something like, for instance, our ALS implementation in MLlib, if you're very careful with how you join, you can scale really well. But if you naively use just the join operations, you're right, it's not going to scale very well. But I mean, that is still a limitation. You have to be very careful with how you're doing it. So, yeah. Yeah.
When you search these large hyperparameter spaces, in addition to the computational problem that you've dealt with, there's also an overfitting problem.
Right.
And specifically, what it means is that your estimate from the data, from the held out data you work with, your held data, out data is not your training data, and it no longer gives you an unbiased estimate of the true error of the system.
Right. So,
do you have a way of dealing with that and integrating it into the whole process so that you get a less biased estimate?
Right. So the first thing I would say is that, so I didn't mention this in when I was describing the plots. All of our results are, we're reporting results on test error. So in some sense, you absolutely are right. As you look at more and more hypotheses, you could be overfitting to, you keep getting feedback on the validation set. Our results are on the test data set. And what we've seen practically is that overfitting is not a huge issue, right? We're looking at the test set once, and the plots seem to work well. If you make the validation set too small, that's an issue. For these adaptive methods, right? So you can overfit to the validation set for a bunch of reasons. One reason is just multiple hypotheses. You can get lucky, multiple hypothesis testing. The other issue is in these adaptive methods, you're actually looking at the previous results to pick the next points, and they're much more prone to overfitting. And we have seen that if you make the validation sets too small there, you actually do see overfitting. For what we've been doing, we have yet to see it. I agree that at some point you're going to hit that as a concern, and it's something we haven't.
It's just going beyond that. There are theoretically motivated results that say, if you're optimizing something, you still should take the point that optimizing, but your estimate of the error should be based on something that's with standard deviation out of there.
Right.
So.
So
the question of the challenge is adding that into the package as another functionality gives you because the package when you do a research project on it, then you find a separate set and you report on that, which is what you did here.
Right.
But as a package, I can imagine a lot of people not bothering with this issue and not really knowing.
And I agree, and I would argue that some of the earlier papers, especially with this adaptive approach, they would report validation error, and we repeated their experiments and actually did see overfitting. So it is something you have to be careful with. There's definitely more work to do there, but we haven't looked into it. We verify that we're not seeing overfitting in our results, and we're careful when we report the results, but we're not augmenting the method to sort of automatically prevent against it. But that would be a good thing to do. Yeah.
I just want to a little better understand the limitations of hyperparameters or how scalable they are. So you reported results on 8 and 16 hyperparameters.
Right.
Did you try with larger number?
So I think 16 is probably the most that we've tried.
So can I be brave enough to try with 50 as well?
You could be brave. Yeah, I mean, the problem gets harder and harder, of course, right? And the argument is sort of, if you push the number of hyperparameters to be too large, then it's kind of this curse of dimension. Your only hope is to downsample. If that doesn't work, you can't do anything anyway, in which case, if the hyperparameter space is super, super large, the argument would be just, try either really aggressive downsampling or aggressive downsampling. Don't try random search because it's not going to get you anywhere anyway. But we haven't, I don't think we've tried on 50 hyperparameters yet, but even with 10 or 12 or 20, it ends up being,
And my other question is, how large data sets did you try? So, for example, ImageNet or...
So we're trying to run ImageNet. It is taking the problem with these experiments are really expensive. Right? So I didn't even actually mention it, but I cheated a little bit in one of the plots that I showed. I cheated in a way that was okay. It wasn't misleading, but which one was it? Oops, sorry. Too much animation. One sec. Right, if I go here, even on Safar, this was, I think, 2 GPU years of computation. And in order to actually run this, we couldn't run it all on the same machines. So what you really care about here is time. We reported a number of iterations because we used a bunch of different machines that were some faster, some slower. The overheads for Hyperband random has no overhead. Hyperband has very small overheads. Adaptive has much more. Qualitatively, the results don't change. The point being, though, that it's super expensive as an academic, even with free EC2 credits and free Azure credits, that we haven't pushed more than this. Internally within Google, the parallel version of Hyperband, they're trying to run with ImageNet, but even that, even running something like that at Google scale is an expensive thing, and it requires a fair number of resources. So it's definitely something we want to look at, but we haven't yet. Yeah.
I think hyperband assumes that the user needs to know the maximum number of iterations in order for the model to converge.
Right.
So in practice, like how does the user choose the number?
Right. So there is a variant of hyperband where so this is the finite horizon version is where we assume that there is a a maximum number of iterations. There is a variant of the algorithm where you can get rid of that assumption. So in theory, you could actually do it either way. In practice, we see that things work much better when you set the max number of iterations. And I would argue that most software packages, they have some pre-built-in max number of iterations. But you're right, you have to have some intuition for how many iterations you want to run.
So in practice, like
Yeah.
does most users use a finite version or the infinite version?
Fine. So we ran all of our experiments with both the finite version, and we have not really tuned the max number of iterations. I mean, it's too expensive to try. So we picked something that we thought was reasonable, 10 passes or 20 passes through the data when we're training a neural network, say. And the finite one seems to work much better than the infinite one.
Yeah, the finite one is
Yeah.
more efficient.
Right. The finite one seems to work better, but you're right. It does require you to set this R parameter. But I don't think it's super sensitive to it, but it is a hyperparameter of our hyperparameter optimization method. Yeah. Okay.
Shall we thank the speaker
Yeah.
one more time?
Thank you very much.